Hello everyone, my name is Mike Allensbach. I'm a PhD student at ASL, and in this part of the fixed wing case study, I would like to tell you a bit about tilt-rotor hybrid UAVs. I will start with a brief overview of tilt-rotor hybrid UAVs, what is reasoning behind the topic and why we're interested in these types of vehicles, and then we will also have a look at the different designs and some application examples. However, I will try to go through this rather quickly so that we have enough time for the actual case study. Here we will spend some time on the difficulty of the transitioning process, have a look at the modeling and control structure, and then finally I will also show you some flight experiments. So let's get started with the overview. Up until a few years ago, there were mostly two different types of aircraft, which were either fixed wing or rotor wing, each with different advantages and disadvantages. Most importantly, we have on the fixed wing side the efficient high-speed flight due to the lift generation of the main wing, which goes hand in hand with being able to carry large payloads. However, these vehicles require runways because we need to be able to accumulate enough speed to generate sufficient lift for takeoff in the first place. On the other hand, rotor wing vehicles have vertical takeoff and landing, as well as hover capabilities, and they are highly maneuverable, mostly thanks to these two properties. On the downside, they are rather inefficient since the entire lift needs to be generated by the rotors, which requires quite a lot of energy. So based on this, the main idea behind hybrid UAVs is to combine the best of both worlds. So to combine the VTOL capabilities of rotary wing and efficient cruise flight capabilities of fixed wing vehicles. Now there exists many different classes of hybrid UAVs, such as tail-sitter, tilt-wing, tilt-rotor, and so on. And then again, each of these has different subgroups with different designs. So here we focus, as I mentioned before, on tilt rotors, and I would like to show you just a few different designs here on this slide. So just start these videos. And so the key idea behind all these designs, and the really key concept behind tilt rotor vehicles in general, is that they can tilt the propellers and only the propellers. This is the important part. So in this part, or in this way, when they can reorient the propeller, they can reorient the thrust either vertically for rotor wing flight or horizontally for fixed wing flight. This can be really well seen here on the left. So we see how the propellers initially are in a rotor wing configuration. So the thrust generation is vertically for takeoff. And then once we transition, we move the propellers forward until the thrust is longitudinal, and basically the lift is now generated by the main wing. So this, what we just saw, is a 4-propeller setup. Then here on the right, we can see the B-22 Osprey, quite a famous aircraft with a 2-propeller setup. And so let me just skip ahead a bit so that you can actually see the tilting. Yeah, there we go. So once again, you can see how the propellers are slowly tilted until eventually we're in a full fixed wing configuration. Yeah, there we go. And then, so just to show you here at the bottom, there's also a 3-propeller design. So as I said, these are just a few examples, and there are many other different designs out there. But in any case, the main idea is always to have some sort of tilting mechanism on the propellers, such that the propellers can be reoriented and such that the overall thrust direction can be reoriented. Applications for these types of vehicles are manifold. So I tried to include just a few here once it loads. Yeah, so one direction, first of all, here on the left, which is strongly investigated at the moment, is urban taxiing and transport. So you can imagine how here the increased maneuverability is particularly useful in urban environments, but especially so when coupled with highly efficient cruise flight for transport. Another example here in the middle is firefighting. So this is particularly interesting since there's currently a focus project going on where the students are also trying to develop a hybrid UAV for firefighting applications. And then finally, on the right, of course, also in search and rescue, we can make use of hybrid UAVs. Here, the efficient flight allows us to cover very large areas, while the hovering capabilities are useful when precise investigation and accuracy in a certain area is required. So as I said, just a few examples to give you some context. Right, so let's move on. Yeah. So with that being said, I would like to start with the actual case study now and start off with a short introduction to the platform that we are considering for the remainder of this presentation. As you can see, this is a 4-propeller setup, and the propellers are mounted on tilting mechanisms on either side of the fuselage here. So on the right, you can actually see the two extreme cases, so to say, of this tilting. So on the top, we have fixed wing mode, where all lift is generated by the wing, and the propellers are only used for longitudinal acceleration. And then the complete opposite would be rotor wing mode here on the bottom, where the lift is actually generated by the propellers, and we have no or negligible aerodynamic effects from the wing. What is important to note here is that the propellers can actually tilt individually. So basically the left side here can tilt independently from the right side, and this will be important later on when we talk about differential tilt. Besides the propellers and the tilting, we also have control surfaces which we can control. So specifically we have 2 ailerons here on the wings, 2 rudders in the back, and also an elevator on the tail. So much for the platform design. I would now like to say a few words about the transition process, which is actually the most difficult part of the entire flight envelope. So as a transition, we denote the flight phase when we have mixed lift generation from both propellers and the main wing, which essentially occurs when changing in between these two flight modes here. Now, during the transition, we need to ensure that we have sufficient lift generation at all times. And as you can probably imagine, this is rather difficult due to these changing lift sources. And so this is also the reason why the transition process is usually done very slowly. However, here in this project, we wanted to have a transition which is somewhat quickly and efficient, while ideally also remaining at constant altitude. Now, the reason why the transition is interesting is because it is not immediately intuitive how to select the most appropriate trajectory during this maneuver. And so I'd like to highlight this problem a bit over the next 2 slides. So as a first example, when going from rotor wing to fixed wing mode, or from helicopter to airplane mode, as it is called here, the main thing that we need to do is to accelerate in order to produce sufficient lift for fixed wing mode. Now, this acceleration can be done, or the initial acceleration at least, can be done in 2 different ways. So either by pitching down, which is shown here on the left, or by tilting the rotors, which is shown on the right. Now, while the pitching results in quite a fast initial acceleration, since also the pitching dynamics of the vehicle is rather fast, it will also lead to downward facing lift forces. So as you can see here, just from the orientation of the main wing with respect to the vehicle velocity, this will create aerodynamic forces which will actually push the vehicle downwards. And so these, of course, need to be compensated in order to maintain altitude. On the other hand, the tilting mechanism on the right here, it has rather slow dynamics, which means that the initial acceleration will be a lot slower than for the method that we saw before. So again, it is not really intuitive at first glance how to perform this transition optimally and how to sort of choose between different methods or how to mix them. And this is mostly due to opposing effects between attitude, aerodynamics, and propeller tilt, as we saw. So something similar, a similar issue can actually be observed when going back from airplane mode into helicopter mode. So here, once again, we want to maintain altitude and transition somewhat quickly and efficiently. But now the main task is actually to slow down the vehicle. And so one way to slow down is to just pitch up basically, and thereby we increase the angle of attack on the main wing and also the drag forces. So this will decelerate the vehicle very rapidly, but it will also cause quite a large increase in altitude, as you can imagine. An alternative is to just start tilting back the propellers. So here we still rely on the drag forces of the main wing, but it's just a lot more gradual than having this aggressive pitching maneuver. Of course, this will result in slower deceleration since we just don't have as strong drag forces as for the left-hand approach. But in turn, it also limits the altitude increase. So to sum up, once again, you can see here these opposing effects that I mentioned before. And once again, determining the best transition trajectory is really not intuitive. And so this was actually the main idea behind this project. So first of all, we wanted to have full control of the vehicle, so develop an appropriate control structure, but also perform some sort of automated transition. So basically what we mean is that we shift the responsibility from coming up with this transition trajectory from the user to the controller. So the controller takes care of how to handle this trade-off between attitude, aerodynamics, and propeller tilt. And we will see later on how exactly this has been realized. Before being able to look at the control structure, we need to first familiarize ourselves a bit with the model of the vehicle. So for this, we start from the basic 6 degrees of freedom Newton-Euler dynamics. So you see here we have the position dynamics, velocity dynamics, quaternion dynamics, and angular rate dynamics. What is interesting here are the external forces and torques, which include, of course, the effects from the rotors and tilt angles here, so the forces and torques from the propellers, as well as forces and torques from the aerodynamics. So this is mostly the lift and drag effects from the main wing, but also the torques from the control surfaces. This is actually shown in a bit more detail in these two sets of equations. So first, for the propeller forces, as I mentioned, these are just the sum of the individual contributions from each propeller. Of course, this is also depending on the left and right side tilt angles. And then, as usual, the torque includes effect due to offset from the center of mass, as well as the propeller resisting torques here. On the aerodynamic side, as mentioned, this is mostly lift and drag effects from the main wing. Then in the torques, again, we have effects due to offset, this time between center of lift and center of gravity. So this is just RA here. And then what is actually more important are the torques from the control surfaces, because this is also something that we need to assign and compute in our controller. So now that we know how the system is modeled, let's see how it is actually controlled. I would like to say a few words here about the general setup and then focus a bit more on the MPC here and the control allocation, since these are the most important components of this structure. As I said, the concept here is that the transition is performed automatically and that the user does not need to worry about how to combine attitude, thrust, and tilt angle commands. So what we supply as an operator is basically just the velocity set point here on the left-hand side. And then the MPC computes the appropriate thrust, tilt angle, and torque commands to achieve this velocity set point, and thereby inherently taking care of the transition. We will see in a second how this is done in more detail. What we also see here is this low-level attitude controller. And actually this entire red box here sort of visualizes the inner loop, which runs at a higher frequency than the MPC itself. And so I will also say a bit more about this later on, but basically the attitude controller is tracking the desired MPC trajectory. And so this helps to improve the overall stability. Finally, as a last step, the commands from the MPC and the attitude controller are fed into the control allocation. And here they are then mapped to the actual actuator commands. So namely, we have the control surface deflections, the tilt angles, and the rotor speeds. So much about the general structure. Let's now move on and have a closer look at the MPC. So once again, the idea here is to let the MPC compute the transition trajectory, and so that the user does not need to take care and worry about the trade-off between thrust, tilt angle, and attitude, which we saw before. Of course, we need to include appropriate constraints and also the system equations of motions in order to make sure that the trajectory is actually feasible. And another nice feature of the MPC is also that we can use a nonlinear solver. And so this way we can really cover the entire flight envelope. So as we saw, the equations of motions are highly nonlinear. And so by including this nonlinear solver, we can make sure that we have as few approximations as possible inside the MPC model. So with that being said, let's actually have a look at how the underlying MPC model looks like. So firstly, I would like to focus on the first 3 lines here. This is actually the system model, which is used inside the MPC. And you can see it is somewhat similar to the model equations, which we saw just before, but there are a few important changes which I would like to highlight. So first of all, in terms of aerodynamics, everything remains pretty much the same. So we still have the lift and drag effects from the main wing here, as well as the corresponding torques. However, now what we do is that the control surfaces and propeller torques have been lumped together into this control input torque here, MMPC. So basically everything that can be controlled by actuators on the vehicle is now combined and collected in this term here. Something similar is done for the forces. So the 4 propeller thrusts and 2 tilt angles have been lumped into this 1 generalized thrust and 1 generalized tilt angles. This combination of terms mostly helps to reduce the dimension of the MPC problem, and in turn also reduces the computation and convergence time. So once again, the equations are more or less the same as before, except that the control inputs of the vehicle are now combined in these new terms. We will later see in the allocation then how the individual actuator commands can be recovered from this. Another point which I mentioned before and which needs to be considered is that the tilt angle dynamics are rather slow compared to the overall vehicle dynamics. So to really ensure that the trajectory that is generated by the MPC is feasible, we need to make the controller aware that, first of all, the tilt angles have certain dynamic, and then second, that this dynamic is somewhat limited. And so this can be done fairly easily by modeling the tilt angle not as an input, but as a state, which is shown here. And so you can then see how the constraints are included accordingly to ensure this or to make the MPC aware of this constraint dynamic. The remaining constraints are just maximum thrust and torque constraints. So these are mostly actuator constraints from the propellers. This is not particularly interesting. Now, after the MPC, as we saw, we have this fast inner loop. First of all, the attitude controller. So I will not say too much about this since the setup is fairly trivial, but again, the idea is that the attitude controller helps to improve the overall stability. So as you can see here, the MPC problem is still rather high dimensional, and it is also non-linear. So the MPC can only run at 20 Hertz, which is rather slow for this type of aircraft, especially in rotary wing mode. And so by using this attitude controller, which actually runs at 100 Hertz, we can track the desired attitude trajectory of the MPC and thereby, as I mentioned, improve the overall stability of the platform. The commands from the MPC, so the thrust, tilt angle, and control torques, as well as correction torques from the attitude controller, are then fed into the control allocation. And so the job of the control allocation is to compute the individual actuator commands, as I mentioned before. So this is specifically the control surface deflections, the tilt angles, and the rotor speeds. The way this is done here is in a so-called daisy chaining approach. So the idea behind daisy chaining is to allocate as much control authority as possible to the efficient actuators before moving on to the less efficient ones. In our case, the control surfaces are more efficient than the propellers, so these are allocated first. And we can see how this is done here. So we basically take the total torque from the MPC and the attitude controller here and allocate it through this matrix, which depends on the individual control surface coefficients here on the diagonal, as well as on the airspeed. Now, of course, the control surfaces cannot be deflected indefinitely, which is why they need to be saturated. And in this case, this is just normalized between -1 and 1. And so any torque which could not be allocated here is this residual torque here is then passed on to the second step of the daisy chaining approach, which is the allocation of the rotor speeds and tilt angles. So you see here, we use the residual torque from the first step of the daisy chaining approach, and we also include the generalized thrust from the MPC. Remember, this is a collection of the 4 individual propeller thrusts, as well as the generalized tilt angle from the MPC, which sort of collects the 2 tilt angles from before. This is a linear system of equations, which can be solved using this pseudo-inverse here. And this actually directly gives us the rotor speeds and so-called differential tilt. I will talk about this differential tilt a bit more in a second, but basically from this we can very easily obtain the actual tilt angles for the left and right-hand side of the wing. So to sum up, this is how we get the control surface deflections, the rotor speeds, and the tilt angles based on the generalized thrust, generalized tilt angles, and torque commands. I would now like to say a few more words about this differential tilting, since this is an important property or feature of this vehicle, which allows us to perform efficient yaw maneuvers during hover. So those of you who are familiar with quadrotors might know that we usually use differential rotor speeds to yaw by making use of the propeller resisting torque. On this vehicle, this can actually be done in a more efficient way by deflecting the tilt angles in different directions on the right-hand side of the on each side of the wing. This is symbolized in this graphic where the thrust of the right-hand side is somewhat pointing backwards, if that makes sense. And on the left side, it is pointing forwards, and thereby we induce a yaw torque on the vehicle. In case this explanation was not entirely clear, don't worry. We can also see this concept very well here in this video. So you can see how the left and right side propellers are tilting in different directions to perform this yaw motion. Again, while the actual rotor speeds remain more or less constant. Yeah. So, but again, this is just a detail about the allocation here. The main concept is really this 2-step daisy chaining, which we see here. Now, probably the most interesting thing to see are the flight experiments with full transition. So this is shown here. As you see, we start off in rotor wing mode. And so we take off basically like a helicopter. And then all we do to trigger the transition, so to say, is to increase the forward velocity set point. So we basically just tell the vehicle to accelerate forward. And then again, so it is the job of the MPC, as you can see here, to compute the appropriate thrust and tilt angles and perform the transition. So let me just show this again. Let's just play it again. So once again, all we do now is basically tell the vehicle to move forward at a certain velocity, and then the MPC will automatically transition from this rotor wing configuration into fixed wing mode, which we can see here. So you can see how the propellers are tilted into full fixed wing mode. And then in order to change back into rotor wing mode, we simply tell the vehicle to stop. So basically set the velocity set point to 0. And then again, so we'll see, you can see here how the propellers have already tilted. And so the vehicle is pitching up very slightly, or actually the MPC commands the vehicle to pitch up very slightly to decelerate until we're then again in full fixed wing mode. So you can see now we have reached hover again. So yeah, once again, I'd like to stress, as a user, we do not have to take care of the transition. This is all done by the MPC. So this was it from my side. I hope I could give you a short overview of tilt rotors in general and of the control and modeling of this particular platform that we looked at. And I would like to thank you very much for listening. Thank you.